And before we prove it, we shall discuss Nahi's question. So what does the unitarity theorem say? It says all finite groups and by extension I should probably put a comma here, extension all compact Lie groups admit representations in terms of finite dimensional unitary operators matrices. Okay, so Nahi, does that answer your question?
Yes, sir, it does.
Okay, so what happens if the group is not finite or if it's not compact? Can somebody give me an example of a very important physics group, Lie group, that is not compact?
The Lorentz group.
The Lorentz group. So can the Lorentz group have finite dimensional unitary representations?
No, according to the theorem, I guess.
Exactly, it doesn't. And that's a very, very important result. And that's actually one of the origins of quantum field theory, is because when we try to marry quantum mechanics with relativity, we come across representations which defy a probability interpretation because unitary representation of the Lorentz group is not possible. And it turns out that quantum mechanics breaks down as we know it. And we are led to a different formulation where the particles of the system are represented in terms of an infinite dimensional unitary representation of the Lorentz group, okay? I've lost the representation. Let me share it again. Okay, so. Unfortunately, we won't be able to discuss those things in a lot of detail, but we shall touch upon them. Okay, now let's prove this theorem. Yeah, please.
So the way you wrote the theorem, it doesn't say that matrices that aren't finite and compact don't have unitary representations, right? It doesn't.
It doesn't say anything about the infinite dimensional cases. It just says that for finite dimension, for compact Lie groups, it admits finite dimensional, unitary representations. Okay. Right. It doesn't say anything about non-compact Lie groups, right? So, but we know that since the Lorentz group is a non-compact Lie group, it cannot have a finite dimensional. Oh, I see what you mean. You might say, well, could it not have the Lorentz group? Could it not have a finite dimensional representation? It is not guaranteed. That's the point. In principle, it could, because this theorem doesn't say anything about that, right?
Yeah, that's what I was thinking.
Yeah, in principle it could, but it's not guaranteed by this theorem. And it turns out, no, that it doesn't. There is no such a, there is, at least it has not been discovered. And I don't think, there may even be theorems about that. I'm not exactly sure, but it's harder to prove these kind of stuff for non-compact groups because the integrals, the sums, they diverge. And it's harder to prove those things. So yeah, that's a very good question. Okay, so we are going to prove this theorem, and after we are going to prove. Hello.
We can hear you, sir.
Okay, I lost you for a moment. Can you hear me now?
Yes, sir.
Yeah. Okay. Sorry about that. Something happened. Everything went silent for a second. Okay, what is happening? Okay, I think this is better. Okay, all right. So, so I'm going to, prove the unitarity theorem, and after that, I will prove another important theorem, and then the rest of the course, there'll be 3 or 4 lectures left after this, maybe 3 lectures left. We will talk about the representation of SU2 and SU3. Okay. Okay, is the plan clear? I mean, if I had more time, if we didn't have like short classes, I could cover more, but we have to do what we have to do. Okay, let's, so we are going to prove this for a finite groups. And the extension to compact groups is by faith. You basically have to say, okay, there exists a Haar measure. What is the Haar measure? The Haar measure is essentially something like, if you have a compact Lie group, you can think of it as a discretized, you can think of a, you can discretize it, right? So, it's a kind of a, version of the Riemann sum, if you. It's not exact, I mean, there are lots of subtleties there I'm glossing over, but I'm going to, give you the proof for finite groups and tell you that it works for the compact Lie groups using the Haar measure.